Okay, so for the first one here, the top equation, where do we start? -5, okay. From there, where do we go? Okay, up 2 over 1. And I'm going to keep going up 2 over 1 just to make sure I get my line relatively straight. Bottom one, where do I start? +2. From there I go down 1 over 3. Where do they cross? What's the point? 3, 1. Perfect. How about over here, top equation? Got to do some rearranging, don't we? What do we have to do to it first? Subtract 2x. So we've got -y equals 3 minus 2x, and then divide by -1. Think of that as a -1y. So you divide by -1. Y equals -3 plus 2x. Where does that one going to start? -3. And from there it goes. Yeah, I think that is 2 over 1, so up 2 over 1. Up 2 over 1. And so on. So next equation, x plus 2y equals 4. What do I do first? Minus x. So 2y equals 4 minus x, and then divide by the 2. Y equals 4 divided by 2 is 2. Negative x divided by 2 is -1/2 x. Where do I start? 2. And from there I go down 1 over 2. So that solution is, not everybody at once, 2, 1. Now for this last one, put a couple equations up there that are a little out of the ordinary. For this first one, y equals 3. Think of it like this, as y equals 3 plus 0x. So where's this one going to start? Up 3. Right? It's got a slope of 0 over 1, so it's going to go up 0 over 1. In other words, it's a flat line. Y equals x. The bottom one is going to start at, I think that was y equals 3/4 x plus 0. So it's going to start at 0. And from there, it's going to go up 3 over 4. So the solution is at 4, 3. Any questions on those? Now I have this y equals 3 here, or y equals a number. And it's pretty easy to make sense of that as being a flat line by adding that plus 0x. But what if I threw out an equation, a system of equations like this? First of all, how do I graph that x equals 6? Well, y doesn't equal anything is the thing with it. It doesn't specify y. What's that? You can go over to 6. Yeah, it's just a vertical line. You know, our graphing, the y equals slope times x plus b, doesn't fit that equation because there's no y there. You know, up here, not having an x didn't affect us. We just add plus 0x and it still made sense. So down there, all we can do is just use the analogy here that y equals a number is a horizontal line. It would make sense that x equals a number has to be a vertical line. And if we look at that, at every point on there, x does equal 6. This would be x equals 6, y equals 4, x equals 6, y equals 6, x equals 6, y equals -1. You know, every point on there, x equals 6. And that's all that's saying is the x coordinate is 6. We don't care what the y coordinate is. Okay, how about the second equation? What are we going to do that one to make it graphable? Subtract 3x from both sides. So this is gone, giving us 2y equals 4 minus 3x. And then divide by 2. Which gives us y equals what? Okay? How do we graph it? Start at 2. Down 3 over 2. Down 3 over 2. Down 3 over 2. What's our solution at there? 6, -7, I believe, right? Now, one thing we should do with these, because graphing can be a little sloppy, we should always go back and test. We said 3, 1 is the solution here. Well, if x is 3, is y 1? Well, 2 times 3 is 6, minus 5 does give us 1. So divide by 1 if x is 6, or x is 3. -1/3 times 3 is -1, plus 2 is 1. So that one works. This one here, 2, 1. If x is 2, is y 1. 2 times 2 is 4, minus 1 is 3. That one works. 2 times 1 is 2, so 2 plus 2 is 4. That one works. Here, y equals 3. Can't get around that. But if x is 4, does that make y 3 in this one? Well, 3/4 times 4 is 3, so that's true. So on all of these systems, you should be taking that solution, put it back in the equations to make sure it works. Any questions? So this is one of the equations we solved by graphing earlier. And we did okay putting it on the graph because it came out to a nice even number. You know, no decimals, no fractions, nothing like that. But if it had a decimal fraction in it, it would be very difficult, well, almost impossible to get that value graphing unless you use some sort of electronic system, like maybe even a CAD system or Mastercam or something like that would work. But working by hand, the only way to get an exact answer if it's a fraction or decimal is to do some sort of an algebraic option. When we look at this, systems of equations by substitution. So when we look at this, we know that the solution to this system is going to be where this y and this y are the same value, this x and this x are the same value. So we can use that to our advantage. The way these two equations are set up, it's actually really easy to do that. Since we know that this y is equal to this y, then the pieces that are equal to them have to be equal to each other. So I can just take those two pieces and put them equal. 2x minus 5 has to equal a -1/3 x plus 2. Now because of that -1/3, this is going to get a little bit ugly, but not terrible. I'm going to have to get rid of one of the x's because there's one on each side. So I'm going to add in 1/3. So we now have 2 and 1/3 x here, minus 5 equals 2. What are we going to do from there? Add 5. 2 1/3 x equals 7. And then divide by 2 1/3. Now, I have people ask me all the time, can I turn that into a decimal and work with it that way? Well, you could try, but it was going to give you a rounded answer. It's going to be a little awkward. Keeping it with the fractions, this will give us x equals exactly 3. If you change that to 2.333 or whatever, you're going to get like 3.01 or something just off like that. So it is best to work with them with fractions in this case. Now that I have that x equals 3, I can go back to one of my original equations and find y. I'm going to use the top one here since there's no fractions in it. Y equals 2 times x minus 5. Well, I now know that x equals 3. So y equals 2 times 3 minus 5. And that's just order of operations. I have to multiply first. 2 times 3 is 6. Minus 5 is 1. So y equals 1. So that gives me the ordered pair. X is 3 and y is 1. Which is exactly what we got from graphing. Now, not every system we're going to work with is going to be as simple as what we had here, where we had y equals and y equals. I mean, we dealt with systems like the second one here, 2x minus y equals 3. And x plus 2y equals 4. In this case, they're not y equals. I can't just put them equal to each other and solve. I have to adjust them. I have to get either y equals or x equals in one of those equations. To do that, I'm going to look for one of the equations that is easy to solve for one of the variables. By easy to solve, the first thing I'm going to look for is variables with a coefficient of 1. In other words, no number in front of it. And there's actually the y here, but that's actually a negative y. That would be just a touch more difficult. There's an x here. That's the one I'm going to solve for here. If there wasn't any coefficient of 1, this next thing I would look for is if they have a coefficient of 2. Because if they have a coefficient of 2, I can divide by 2 and I'm just going to get a half or 0.5 if it's an odd number. From there, I would jump to 4. Why would I skip 3? Because if a variable has a coefficient of 3, if I divide by a 3, do I get a nice even decimal? No, I'm going to end up with fractions. Now, if you don't mind working with fractions, go ahead, divide by 3. But I'd jump up to 4. Then 5 is easy to divide by. Then I'd probably jump up to 8 from there because 6 and 7 both could be really ugly decimal. They're non-terminating decimals, so you'd have to keep them as fractions. Hopefully we don't have to go too much above 5 to figure out something to solve for. Here we have this x all by itself, so it's a coefficient of 1. So now I'm going to solve for that variable. I'm going to solve for x in this equation. How do I solve that equation for x? The 2y is added to it, so I'm going to subtract 2y. So x equals 4 minus 2y. You'll notice what I just did here is the opposite of what I did up above when I was solving to graph it. Up above, I solved for y. So I had to subtract the x and divide by 2. When I'm doing substitution, it doesn't matter which variable I solve for. I usually try to find the easier variable to solve for. So in this one, I'm solving for x. So now that I've solved it for that, x equals 4 minus 2y. I go into the other equation and I replace x. Here's x. So instead of 2 times x, it's going to be 2 times x equals 4 minus 2y. So I put 4 minus 2y in where the x was. Minus a y. equals 3. So now I've reduced those two equations down to a single equation with one variable. And when we're talking about algebraic methods of solving systems of equations, that is, no matter what method we're using, that is our strategy, is to reduce those two equations with two variables down to one equation with one variable. And then we can solve it. What's the first thing we have to do here? Parentheses, right? Exactly. We distribute the 2. So 2 times 4 is 8. 2 times negative 2y, negative 4y. Then we still have the minus y there, and equals 3. Now, is there anything we can combine here? We got negative 4y and minus y. Think of that as a minus 1y. That makes negative 5y equals 3. Then what? Well, now I just have y appearing once. Now I can solve for y. What do I have to do to solve for y here? Subtract 8. It's a positive 8, so I have to subtract 8. So I have negative 5y equals 3 minus 8 is a negative 5. And then divide by negative 5. Y equals 1. Once we have y equals 1, just like we did in that first example, we go back up to our original equations, and in one of these equations, we have to replace y with 1. It doesn't matter which one. So I'm going to take the top equation, I'm going to put y equals 1 in there. So 2x doesn't change, minus y becomes minus 1 equals 3, and now I solve. I'll add 1, 2x equals 3 plus 1 is 4, and I will divide by 2. X equals 2. So x equals 2 and y equals 1. So it gives me the ordered pair 2, 1. What do you think? Let's do a couple more examples.
How do you know when just looking at it? When you can,
What's that?
how do you know, but just looking at it, when you can combine the equations and when you have to substitute?
Here, I'll show you in just a second here. What do you mean by combining them?
Like,
Okay.
like the first one?
Well, like here, they were both y equals.
Oh, okay.
Technically, what I did is I did substitute. I took y equals this,
Yeah.
and y equals this. I took that 2x plus, or 2x minus 5, and I put it right here for y. I replaced that y. It's just down here it wasn't nice and neat. The x is actually in the middle of the equation instead of off on its own.
So if it's both of them are y equals,
Yeah, then you're replacing one of the y's with just the other equation.
you are substituting.
You are substituting, yes. So now looking at this one, I have to pick a variable to solve for. I do have the negative y there, would be okay to solve for. And I have a 2x on top and a 2y. Either one of those would probably be okay to solve for. They'd just give me a half or a 0.5. I am going to solve for this one here, the y. I should just circle the y because I'm going to have to get rid of the negative. But I'm going to treat that as a negative 1y. So I'm going to bring it over here and I'm going to solve for y. So this is 2x minus 1y equals 11. To solve for y, what do I have to do? Subtract 2x. So that's gone. Negative 1y equals 11 minus 2x. And then divide by negative 1. So y equals a negative 11 plus 2x. So that came from this equation. So I have to put it back into this one for y. So 3x plus 2y, but y now becomes, I put it in parentheses, negative 11 plus 2x. That equals negative 1. So now I solve. I have to deal with my parentheses. So 3x up here doesn't change. Positive 2 times negative 11. Negative 22. Positive 2 times 2x. Positive 4x equals a negative 1. And then 3x and 4x make 7x minus 22 equals a negative 1. And then add 22 to both sides. So 7x equals 21. And then divide by 7. X equals 3. So we now know x equals 3. So I can go back up to either one of my original equations and replace x with 3 and solve for y. But I'm going to show you a little trick. It's a little easier if I go back to this one here that I solve for y. Because now I can just plug in an x. Y equals negative 11 plus 2x. Well, I just found that x equals 3. So I put 3 in where the x is. So order of operations here says I multiply first. 2 times 3 is 6. So that's negative 11 plus 6, which is negative 5. So x equals 3, y equals negative 5. What do you think?
Go back up once.
Okay.
Up a little higher. Okay, let's substitute 3 into 2x. Somehow I got negative 17. Or the top equation.
The top one up here.
Y.
So 6 minus y. You got to subtract 6, you're going to get 5, right?
Oh, I didn't subtract.
You added it because you treated it as a subtraction. Yeah. Yep, yeah, I remember it's a negative 1y. Yeah. That's actually a common mistake. People do that a lot of, oh, it's x minus y. I'm just going to add x because it's being subtracted, but it's the y that's negative. So, I got a system like this. But the only one that's easy to solve for is y up here in this top equation because it's got a 2 in front of it. So let's do that. Solve that for y. That is one of the things with substitution. Usually, unless you have an equation that's already set up as x equals or y equals, usually you're going to have to pick an equation and solve for one of the variables in that equation. And you'll get good at picking out which ones would be easy to solve for and which ones wouldn't be.
But they all work.
They all will work. It's just how ugly of fractions you want to work with in the process. So I'm going to solve this for y. I have to subtract 3x first. 2y equals 8 minus 3x. And then divide by 2. Y equals 4 minus 3 halves x. So that has to go in here for y. So this is 6x plus 4 times 4 minus 3 halves x equals 7. So I have to multiply through by the 4 here. 4 times 4, 16. 4 times a negative 3 halves x, negative 6x. Now what? 6x and negative 6x make 0x. It cancels out. So I got 16 equals 7. What's that mean?
Doesn't work.
It doesn't work. Are there any values of x and y I can put in there that make 16 equal 7? No. If I were to graph these two equations here, the top one, I'll put in blue, would look something like this. The bottom one, put in light brown, would look something like this. Why is there no solution to that system? They're parallel. They never cross. Let me show you another case here. Now I made this top one easy to solve for x. Just a side note, it won't always be the top equation. It just the last couple of examples have turned out that way. So I'm going to subtract 5y. X equals 3 minus 5y. So what do I have to do with that? Put in the bottom one for x. So 2 times, instead of x, I'm putting in 3 minus 5y. Now I got to deal with the parentheses. 2 times 3, 6. 2 times negative 5, negative 10y, plus 10y, equals 6. And then, negative 10 and 10 cancel out. Yeah, 6 equals 6. Same type of thing happened as well up above. Does that mean there's no solution? Well, does 6 equal 6? Yeah. Are there any values of x and y I can pick that'll make 6 not equal 6? Now, when I say all numbers x and y, that's a little misleading. I should probably word it more like this. Those are the same line. If I were to graph those, that top equation, x plus 5y equals 3, is going to look like this. That bottom equation, 2x plus 10y equals 6, is going to look like this. They're the same line. So technically the solution is every point on the line. So my solution is just one of the lines. So I could rewrite the equation of one of the lines. Any point that's on that line is also on the other one, so the solution. So this is infinitely many solutions. For this one was no solution. Now in both cases, the variables canceled out and disappeared. So how do I know which one's no solution and which one's infinitely many solutions? Yeah, this one, we had two numbers that were not equal to each other. There's no way that's ever going to be true, so that's no solution. This one, we had two numbers that do equal each other. That's always going to be true, so there's infinitely many solutions there. For homework, in the big book, we're going to have you work on page 411, exercise 17-2. Substituting them in. Some of those can get ugly.